So quantum mechanics is our best theory of the very small, of atoms, electrons, quarks, nuclei, the Higgs boson that they found at CERN and so forth. And because large things are made of smaller things, because matter as a whole is made of subatomic constituents, then to say that quantum theory is our best theory of the very small constituents of the world is basically to say that quantum theory is our best theory of pretty much everything. And by a lot of standards, it's the sort of shining success story of physics. It has predictive power from scales ranging from the very smallest constituents of the universe to the pattern of the very earliest radiation from the Big Bang. It's responsible for vast amounts of modern technology, including the computer and the personal phone. It's been tested in an extraordinary range of circumstances. It's never got a test wrong, and some of those tests have been an accuracy of 1 part in, I think, about 10 to the power of 12. Some of these tests are better than measuring the distance to the moon to a higher accuracy than the width of a human hair. So suffice it to say, this is quite a good theory. From another point of view, it's the scandal of modern science, because a basic starting point of what we want a scientific theory to be, you might think, is that it's supposed to give us an account of what's really going on in the physical world. It's supposed to actually give an explanation for why it is that we see the observed phenomena in the world behave the way they do. And most of our theories work that way. You know, our best theories to explain why we see the fossils we see give us an actual story about what was happening in the world that caused the fossils to be laid down. Our best theories as to why we see the lights in the night sky give us a story of stars and galaxies that's responsible for explaining why those lights are there. Quantum mechanics doesn't seem to do that. And what I really want to do for the first part of this lecture is try to explain in non-technical terms why that is, and why there seems to be something profoundly puzzling about quantum theory. And what I'm going to be spending the rest of the lecture and the next lecture trying to make the case for is that when we think about quantum mechanics, to recover our understanding of the theory as an account of what's going on in the world, we're forced to, or led, if you like, to some discoveries about the world, some theories about the world's scale and the amount of it that's hidden from us that are fairly radical, and yet in a certain sense are fairly conservative, because they just come from thinking hard about our best physics and applying our best philosophy to our best physics. So let me start illustrating how that works. I'm going to talk through a few very simple experiments. Now, I should have a disclaimer, since I think there are some physicists in the audience here. I originally started as a theoretical physicist, and then that started to sound a little bit too practical. So I decided to move into philosophy of physics. So my acquaintance with actual pieces of experimental gear is not great. And so my description of what's going on here is going to be on the schematic side. So suppose we have a laser beam that generates a beam of monochromatic light. A laser, by the way, is another example of something that we can't understand without quantum mechanics. And the laser is picked up as a detector. And that's fine. The detector just registers the intensity of the laser light falling on it. But we can imagine turning down the strength of the laser beam. We put some kind of screen into the beam, or we adjust the power into the beam, or similar. And we might expect to find that the intensity of the laser light detected just goes down very smoothly to 0 as we reduce the power of the laser, or we increase the opaqueness of the screen we put between the laser and the detector. And up to a point, that is what we observe, but after a while it stops being what we observe. And what we find is that the light coming from the laser is only detected in chunks. So there's a particular minimum amount of energy, a quantum of energy, such that we never detect red laser light of less than that chunk of energy. And in fact, such that whenever we detect red laser light, it's an integer multiple of that chunk of energy. So the natural thing one is led to think there, and this is actually the thing, not the theory of relativity that got Einstein the Nobel Prize, one's naturally led to think that light itself comes in chunks, and to give those chunks a name, and we call them photons. Okay, so far so good. Now let's make it a bit more complicated. So this is what physicists call a half-silvered mirror. It lets through half the light, it reflects half the light. So we take the beam and we shine it onto one of these half-silver mirrors and we split the beam in two. Then we put in a couple of ordinary mirrors so as to bring the beam back so the two beams cross again. In the crossing, we put another half-silver mirror so that this beam of light is split in two and this beam of light is split in two, and the two pairs of beams overlap with one another. We put a detector in each of the beams, and I'll give them some labels so I can talk about them. So what might we expect? Well, here's something we might expect. We might think, well, we've just discovered that light is made of particles. Light is a stream of particles. So when we say that half of the light bounces off the half-silver mirror and half of the light goes through, the natural thing to think is, well, each photon has got a 50% chance of going through the mirror and a 50% chance of bouncing off it. Half the photons go along the left beam and half the photons go along the right beam. And of the half of the photons going along the right beam, we'd expect half of those photons, a quarter of the photons in total, would go up towards the A detector, and a quarter of them would be deflected towards the B detector. And likewise, of the half of the photons in the left beam, we'd expect half of them, a quarter of the total, to go towards A and half to continue towards B. And so in total, we predict that half of the laser lights detected at A and half the laser lights detected at B, and this splitting hasn't done anything very interesting. Well, if that were true, this would be a short talk. What we actually find is that depending quite delicately on how you set up the experiment, and in particular on exactly how long the paths are that the two laser beams take, we can actually arrange for all of the detection to be at A, all of the photons to be found at A, or all of them to be found at B, or anything in between those values. And this is called interference. Okay, so how could that be? Well, here's a thought. Half the photons are going through the right-hand beam, half the photons are going through the left-hand beam, and the ones that are going through the left-hand beam are colliding with the ones going through the right-hand beam. They're interacting in some way, and as a consequence of that interaction, some of them are swerved from the trajectories they would have taken if it wasn't for the other photons in the other beam. Sounds perfectly plausible. Well, that's testable. If that theory is true, we should be able to turn down the intensity of the laser until only one photon's going through at a time. And then that one photon is going to have gone either along the right beam or along the left beam, and there won't be a photon on the other beam for it to interact with. So the prediction would be that as we turn down the intensity of the laser, the interference effect will go away, and we'll go back to that 50-50 prediction we made at the beginning. That's not what happens. In fact, no matter how low we set the intensity of the laser, the interference pattern will continue quite unabated. If we set the experiment up so that all the light goes to A, then even if we turn the intensity of the laser so far down that only one photon goes through every 10 minutes, we're still going to find that all of those photons end up at A and none of them go to B. Okay, so maybe each individual photon breaks in half, and a half of the chunk of energy goes along the left beam, and a half of the chunk of energy goes along the right beam. Because it certainly sounds a lot from what I've described, as if somehow something is in the left beam and simultaneously something else is in the right beam, even when there's only one photon going through. Well, we can test that too. Instead of doing the interference, we'll just put our detectors straight in the beam. If that theory is correct, what we would predict is that what we find in each detector is that the chunks of light we detect are half the usual energy strength of chunks of light produced by the laser. These will be some sort of half-strength photons, half-energy photons. And we'd also expect that every time we send a photon through the system, we find a half photon here and a half photon here. That's not what we find. Whenever we find a photon, we always find it at full strength. We never find any of these mythical half photons. And we always find either the photon turns up here and there is nothing here, or the photon turns up here and there is nothing here. I'm going to insert a brief disclaimer there for anyone who actually knows any laser physics. Setting the experiment up quite that well is incredibly difficult. But in the abstractions that are permitted to theoreticians and to philosophers, then things behave as I've just described. Okay, so let's go back to the original display. What is going on? It looks as if somehow there has to be something in the left-hand beam and something in the right-hand beam at the same time. Furthermore, it looks like the something in the left-hand beam behaves just the way that a photon does. It passes through those things which photons pass through. It's blocked by those things which block photons. It's reflected by those things which reflect photons. The thing in the right-hand beam seems to do exactly the same things. But when we ever have a look to see what's in the beam, all we ever find is a photon in the left beam or a photon in the right beam. The best imperfect description of what's going on we can give is to say that somehow the photon is in the right-hand beam and the left-hand beam at the same time, not split in half, but somehow is entirely in the left beam and entirely in the right beam at the same time, and that somehow, nonetheless, when we measure where it is, all of that strange simultaneity of photons in both beams goes away. And I'm going to show you just a little bit of the way we write this symbolically. Here's a formalism that Paul Dirac introduced to describe these ideas back in the 1920s even. So this slightly strange symbol we call a ket, which is sort of like a half bracket, is just supposed to be the way we'll write a photon that is approaching the A detector. So if the state of the whole physical system is photon approaching the A detector, we'll write that little blue A to represent it. And we'll write the little blue B to represent a photon, this is a typo of course, I'm sorry, approaching the B detector. And quantum theory tells us that photons can be in what we call superposition states, which are of the form some part of A plus some part of B. These are actually complex numbers, but it won't really matter for my talk if you just think of them as numbers. And so the physics has a perfectly good mathematical formalism to describe these superposition photons that are in both places at once. And it also has a perfectly good algorithm, what the physicists sometimes call a shut up and calculate rule, to go from these ideas to knowing what to actually predict if you do an experiment. And the rule is this: take the number in front of the A state and square it. It's a complex number, modulo square it really, but take the number and square it. That's the probability that the photon is measured by the A detector. And the other number, E, is the probability the photons is detected by the B detector. And as soon as you see this kind of notation, the tempting thing is to say, well, when I ever write down something like A big A plus B big B, I'm really just expressing that I don't know where the photon is. I'm really just saying, well, maybe it's in the A state or maybe it's in the B state and I don't know which. But remember, we've seen that can't be what's going on. We've seen that we can't understand the interference experiments merely in terms of probability. Because if the photon was in the left-hand beam, then it would be split and it would go half to each detector. And if it was in the right-hand beam, it would be split and go half chance to each detector. So if we simply don't know which beam it's in, so to go back to the diagram, if we don't know whether the photon is here or here, it doesn't matter. Because if it's here, we know it'll be split, and we know we're going to signal there half the time and there half the time. And if it's here, we know exactly the same thing. So without knowing which beam it's in, we can still predict that we'll get a detection at A half the time, detection at B half the time. And we know that's not what happens. So whatever this thing is, whatever this superposition is, it can't be any kind of probability thing in itself. It can't in itself simply express our ignorance of the photon. And yet it connects to our experiments through this rule, through a rule that says that thing is to be understood as a probability. We can take this weirdness and turn it more or less into paradox. Suppose we think, okay, those detectors that I wrote on the board, in reality, they're schematic for bits of machinery, bits of kit, made up of atoms and molecules and electrons and obeying the laws of quantum theory. So we ought to be able to ask, what, according to physics, happens when we look to see where the photon is? And qualitatively, here's what the physics says. Here's what our equations say. They say, well, when there is a photon in the left-hand beam, the photon detector, sorry, when there's a photon in the A beam, then the A photon detector clicks and the B photon detector doesn't click. If that wasn't true, these wouldn't be good functioning detectors. And if the photon is in the B beam, then the A detector doesn't click and the B detector does click. So if the photon is in this superposition state of being in the A beam and the B beam at the same time, then the physics says that at one and the same time, firstly, the A detector clicks and the B detector doesn't click, but also secondly, the A detector doesn't click and the B detector clicks. That doesn't even seem as if it makes sense. And here's how that goes in this strange notation of Dirac's. If I use 0 with a delay next to it to reflect the state of the first detector before it goes off, and then 1 with a delay next to it to reflect the same state of the detector, that same detector after it's gone off, then here's what had better happen if the photon's in the A channel. So initially, the photon's in the A channel, as in the A, the route going towards the A detector. Both detectors are raring to go. They haven't clicked yet. The system evolves. The photon just gets absorbed, ignore it. The first detector clicks, the second detector doesn't click. And in the B case, and again, I clearly can't type, this is a B. In the B case, we get first detector doesn't click, second detector clicks. So if it's in a superposition, and here for physicists and mathematicians, I'm using a basic fact about the equations of quantum mechanics, they are linear. The photon is in this strange superposition, A state and B state at the same time. Shove it through the mathematics here, and we find we now have a superposition, not of a photon in two states at the same time, but of the detectors in two states at the same time. The superposition is now a superposition of the first detector clicking and the second one not clicking, with the first detector not clicking and the second one clicking.
Is there another typo here?
Yes, you're right. I'm making a mess of this, aren't I? Yes, indeed. These should be inverted.
1A, 0B.
Exactly, thank you. It's funny, no matter how often you check these things, you look straight past the errors in them. You're quite right, thank you. The point is that I have these two macroscopically different states, representing macroscopically different states of affairs. The equations tell me that both of them are there at the same time. There's a famous and very vivid way, perhaps not very ethical way, of making sense of this that goes back to Erwin Schrödinger. Schrödinger says, right, it isn't quite his example, it has the same effect. Hook up the A detector to a flask of cyanide gas. Put the flask of cyanide gas in a box with my cat. If the A detector goes off, my cat dies. If the A detector doesn't go off, my cat lives. So if the A detector goes off and doesn't go off at the same time, my cat lives and dies at the same time. The Schrödinger's cat is somehow alive and dead at the same time. It's not clear what it would even mean to say that a cat is alive and dead at the same time. Even if we did understand what it would mean, then it doesn't seem to be the sort of thing cats do. So something seems terribly wrong with this theory that I was telling you was so good. Pragmatically, it's fine. We just ignore the equations whenever we want to get the answer out and just use the probability rule I gave you earlier. But in terms of understanding what's going on, we seem to have a profound problem. And there's sort of, outside the topic I'm going to tell you about, there's sort of been two ways of trying to resolve these problems, which you might call the change the physics strategy and the change the philosophy strategy. So the change the physics strategy basically says, well, if the equations of quantum mechanics are delivering these kind of results, then so much for the equations of quantum mechanics. Never mind if quantum mechanics is so successful, it must nonetheless be wrong. We need to alter the equations, we need to supplement the equations, we need a new theory. And there have been a few people in physics who've tried to develop theories of that kind, but for the most part, the change the physics strategy is very popular among philosophers. Change the philosophy strategy says, well, look, You've got into this line of thought because you've just been assuming that scientific theories are trying to tell an objective, third-party account of what's actually going on in the world. Quantum mechanics, says this strategy, tells us something different. It tells us that consciousness plays an essential part in physics, or that scientific theories aren't really in the business of telling us about the world. They're just gadgets to predict the results of experiments. Or logic can't be used as cleanly as we're using it. In one way or another, our basic philosophical framing, which seems to works fine for basically the rest of science, somehow needs to be modified for quantum mechanics. And while there have been a few attempts in the philosophy literature to develop strategies of this kind, by and large, the change to philosophy strategy is very popular with physicists. So what's the alternative? Let me tell an analogue. So Ludwig Wittgenstein, this is one of these stories that's almost certainly not true. It's too good to be true, really. But supposedly, Wittgenstein was in the quad in Cambridge with a colleague, and Wittgenstein, as was his wont, asked the colleague, why was everyone so surprised to discover that the Earth went around the sun? And the colleague said, looking a bit puzzled, well, it looks as if the sun goes around the Earth. And Wittgenstein thought for a minute, and he said, well, what would it have looked like if it looked like the Earth went around the sun? And the answer, of course, is it would look like things actually look, because this is how things actually look, and the Earth does go around the sun. And the reason why we think that seems so strange is that our sort of way of trying to work out what it would look like if it looked like the Earth went around the sun is sort of based on a sort of intuition that we'd feel the air rushing past as the Earth whipped around the solar system, and it would just be very dislocating and disturbing. If the Earth was moving, we'd just be vividly aware of it, and we're just intuitively and immediately aware the Earth can't be moving. Well, the lesson of Galileo is that our intuitions are not actually such a great way to work out what would happen in some observational situation. If you want to know what it feels like to be in a certain situation, if you want to know what empirical evidence would be of a certain theory being true, don't consult your intuition, consult the theory. So a parallel line of reasoning to Wittgenstein's was developed by Hugh Everett from 1957 onwards. So go back to Schrödinger's poor cat. What would it look like if it looked as if the cat was alive and dead at the same time? Well, I think my intuition of what it would look like if I saw a cat that was alive and dead at the same time is I'd somehow be like seeing double, or be like being ridiculously drunk or something. I'd somehow see a blurry image of a live cat and a dead cat. That's my intuitive feeling of what it would look like. So much for intuition. Here, in what, to be fair, is a fairly heavy paraphrase, he doesn't use this example, is Everett's observation on this. What would it look like if it looked like the cat was alive and dead at the same time? Everett went to the theory. What does the theory say about what happens when you look at a cat that's alive and dead at the same time? Well, if I look at a cat that's alive, I'm just one more physical system. My process of observing a cat is a process of my transitioning from one state to another. So I start off in a state where I don't know if the cat's alive or dead, and I transition into a sad state where a happy state where I observe it's alive, assuming I like cats. Likewise, if the cat's dead, observing the cat causes me to transition into a sad state of seeing the cat's dead. So according to the physics, observing a cat that is alive and dead at the same time causes me not to transition into a state where I see double, but to transition into a superposition of states myself. I too end up in a superposition. And I'm now in a superposition of seeing a live cat and seeing a dead cat. And if I then go and talk to Marianne about this and report the situation, she in turn is in a superposition of being told the cat is alive and being told the cat is dead. And if it's then broadcast on Oxford University's website, then the university's website is now in a superposition of describing the cat as alive and describing the cat as dead. And this superposition, this indeterminacy, spreads outward very fast. Here's this in the formalism of the theory. So if I write ready to be my physical state before I look at the cat, then here's what happens when I look at the cat. I go to the combined state of me and the cat goes to cat alive, I see live cat. Wait with interest to see what my next typo is. And likewise, if the cat's initially dead, then I transition into this state where the cat's in the dead state and I'm in the seeing dead cat state. So the superposition, if I look at the superposition, then the system of me and the cat jointly goes into this joint state where each of the individual terms in the superposition is a perfectly normal state of affairs, but both are present simultaneously in the superposition. And it's that that spreads out. So the quantum mechanical state of the entire planet within a very short time of the cat ending up in its live plus dead state is actually going to be a superposition of two terms. Each of those terms is going to look like a perfectly ordinary macroscopic set of goings-on involving a living or dead cat. The whole of them are superposed together. The terms in the superposition are not really affecting one another. You recall that the reason we wanted these superpositions in the first place was to engage with the phenomena of interference. But doing interference experiments with photons is doable. Doing them with lots of photons is quite tricky. Doing them with cats is basically impossible. So as a practical matter, the interference effects, which effectively link up the goings-on in the different branches, not link in a straightforward way, because it's, again, for mathematicians, it's linear, but leads to there not being independent goings-on in the two terms in the superposition, go away once the superposition gets large like this. So then, Everett's suggestion in modern terms is that if we just take quantum mechanics seriously and don't modify it, and if we don't think in terms of the theory requiring external observers or external consciousness or just being a calculus for experiments, but we really take it literally, what the theory is telling us is that quantum mechanical measurements cause the world to branch into parallel streams, which we give the somewhat picturesque name of worlds. So the sense in which the theory is a many worlds theory is it's a theory of many parallel non-interfering goings-on. How many? Well, we don't make that many explicit quantum mechanical measurements, but many, many phenomena in the natural world demonstrate quantum mechanical randomness, whether directly, as in when you observe the flickering of a fluorescent light, or indirectly, as in where the chaotic and unpredictable nature of the dynamics of the weather cause tiny, tiny instabilities to be magnified up so that whether or not it's sunny, well, it's England, so forget that example, whether or not in Spain it's sunny on a given day depends on quantum mechanical indeterminism months or years previously. So this kind of thing is going to be happening an awful lot. In one sense, in the fundamental sense, we only live in one very large, very alien universe, according to quantum theory. But in an emergent sense, we live in a world where there are many, many copies of us constantly being branched from one another by the magnification up to the macroscopic scale of quantum mechanical superpositions of this kind. Okay, so that comprises my introduction to the topic. What I'm now going to do is lay out the main philosophical difficulties in taking the rather qualitative sketch I've given you and make it into something that's philosophically robust and solid as an understanding of quantum mechanics. I'm going to pass fairly lightly over the technical and mathematical aspects that it also involves, but I'm happy to talk about them in the discussion after this talk or the next. So here are what tend to be regarded as the two main problems of this approach. In fact, let me, before giving you that, give this approach a name. Hugh Everett came up with it. It tends to be called the Everett interpretation. Its somewhat more glamorous name, though in some ways a little more misleading, is the many worlds theory. But I'm going to be talking here mostly about the Everett interpretation of quantum mechanics. And by that I'll simply mean quantum mechanics taken literally, unmodified, following it where that leads us. Here are the two problems. The first you might call a problem of ontology. I've given you a sort of rough sketch, and the mathematics gives us a rather sharper sketch of how quantum mechanics leads to macroscopic scale superpositions, superpositions where each term in the superposition has the same kind of structural features as the quantum states we would use to describe whole worlds in some macroscopically fairly definite state. But are we entitled just because the quantum mechanics says we have a superposition to talk about multiplicities? Was I really licensed to go from saying, I see the cat alive and I also see the cat dead at the same time, to saying, there are two versions of me, one of them sees the cat alive and one of them sees the cat dead? For various reasons in the earlier literature on this subject, people often called this the problem of ontology. Sorry, the preferred basis problem. Problem of ontology is more my term, and I think gets a little more at what the relevant issue here is. I can pick up on that in the discussion if it's useful. The second problem is the problem of probability. I told you at the beginning that the way quantum theory works, from an experimenter point of view, is that it's a random theory. I get such and such result with probability 41%, such and such result with probability 59%. Those probabilities are inherent in the application of the theory. They're written into the rules by which we use the theory. In particular, they're written into that rule I gave you that says if you want to get the probabilities off from the quantum state, square those terms at the front, those numbers in front of the states. But the theory I've described to you seems to be deterministic. It's a theory whereby if I make a quantum measurement, I don't randomly get one outcome or the other, I deterministically get both outcomes at the same time. So there's a deep question as to how this theory of deterministic branching can experimentally look like the theory of random goings-on that we experience in the laboratory. I'm going to talk about that second problem in the second of these lectures, I think this evening after supper. There might be thought to be a third problem, which you might call the problem of absurdity. Or the problem of you've got to be kidding, right? Isn't this ridiculous? Ludicrously ontologically excessive? Absurdly counterintuitive? I'm going to talk about that problem at the end of either this lecture or the next, depending how my timing goes. I promise to pick it up at some point, so if you're currently sitting thinking, well, wait a minute, why are we even taking this seriously, please? Don't worry, I am going to say something back to it. Although I don't think you're going to like it. Let's talk a bit about that problem of ontology. Here's Adrian Kent, physicist in Cambridge, long-standing researcher on foundational interpretationalism in quantum mechanics and long-standing critic of the many worlds theory. Puts it very nicely like this. This is his way of putting the problem of ontology. One can perhaps intuitively view the corresponding components of the quantum state, that is, the terms in the superposition, as describing a pair of independent worlds. But this intuitive interpretation goes beyond what the axioms justify. The axioms say nothing about the existence of multiple physical worlds. So Adrian's concern is to say, look, if the theory is really a many worlds theory, shouldn't the many worlds actually be in the mathematics of the theory? If you're really saying the world is constantly branching into many, many parallel copies, where in your equations is the explicit description of the way in which the world branches into parallel copies? If it's not, says Adrian, in the equations of your theory, then all of this talk about many worlds happening is loose talk, metaphor, perhaps even illusion. And I think there's a sort of tacit in this criticism, there's a sort of dilemma that's been suggested for the proponent of anything like this sort of branching reality. Either your branching structure must be fundamental, or it must be illusory, perhaps in the mind at best. But I think that's a false dichotomy. It's fairly easy to think of objects which are not represented in the axioms of our most fundamental physics, and yet which we regard as completely and unambiguously and objectively real. Here's one. Tigers, I take it, are physically real systems. However, if you look at the equations that govern the standard model of particle physics, which is our best current theory or specific theory of quantum mechanics, you will find terms in those equations describing electrons, quarks, photons and gluons. You'll find a term describing the Higgs boson. There isn't a Tiger term. And of course, the reason for that is a Tiger is a very large, high-level complex system. Now, it's not crazy philosophically to think that physicists and chemists and biologists overreach in supposing that it's ultimately a microphysical system. But our general consensus, and what I'm going to assume without further argument in this talk, is that ultimately it really is the case that the full behavior of tigers is determined by the physical behavior of the bits and pieces inside tigers. But let's ask then, suppose you've got some, I don't know, 10,000 square mile area of some national park where you'll find tigers. And let's suppose you want to study hunting patterns of tigers. You've got a big research grant and you want to study tiger hunting patterns and get a good, solid theoretical understanding of it and check it against experiment. How might you go about doing it? Well, here's one. You could say, fine, the tiger is made up of electrons and subatomic particles. We know the laws of physics that govern all of those. That's also true for the grass and the deer they eat and so forth. So I'll do a very, very large, very, very complicated computer simulation of all of the equations of the most fundamental physics applying to this system, and I'll work out what happens. And I take it that's crazy. And there's sort of two reasons why it's crazy, and this speaks to sort of general questions in philosophy about what it means to explain something. Here's one reason it's crazy. It's vastly, vastly beyond our empirical capabilities. There is no plausible way we could actually learn the locations of every atom and every electron and every molecule and every photon in the entire national park in order to plug it into our equations. Even if that was the case, we have nothing like the computational capability to actually solve those equations in full exactness for all of the particles in the national park. So that's one reason why this strategy is insane. But there's a much deeper reason. Suppose we were able to do that. So we take the, what's that? I think there's one called this. We take the Kanha National Park in India. We've built a device that is so clever that it can record the positions of all of the particles in the Kanha National Park and run forward and thus deduce the positions of all the particles in the Kanha National Park an hour from now. Okay, I just said that there is no possible way we could build a machine that could do that, but actually that wasn't quite true. We actually have a machine that does that extremely well. It's called the Kanha National Park. It runs in real time. But it doesn't give us any explanation. It doesn't actually tell us why the generalizations that apply to the tigers and the antelopes and the like actually hold. It doesn't give us the high level of understanding we were after. Here's a little analogy to that. We have some very good laws of physics for how gases behave when you squeeze a gas cylinder. We know that the more you squeeze it, the hotter it gets, the higher the pressure gets, and there are equations governing this that should be known for centuries. We also know the physics, or at least at the level necessary, the physics of the atoms inside the gas. And so you can coherently ask the question, well, given that we know the physics of the individual atoms in the gas, why is it that we, why is it that we carry on using the equations for the gas as a whole, for those equations about how the pressure and temperature are related? And there's an answer you'll often see in undergraduate textbooks, which is that the reason we do it is that it's too difficult to learn the locations of all the particles, and it's too difficult to solve the equations for all the particles. So the reason we use that high-level equation linking pressure and temperature is all about our ignorance and limited capabilities. But you can imagine space aliens arriving on Earth and wanting to be helpful. And when we explain our physics of gases to them, and we explain why we do this because we're just limited, the aliens say, oh, well, that's great. We have very advanced technology. We can work out where all the particles in the gas are. Here's a big book telling you the answer. And we've got a big computer that can work out where the particles in the gas are going to move. It's not as if we had all of that, we wouldn't still find valuable that generalization between pressure and temperature that governs the gas. Because what we want to understand is why it is that we find these general properties governing systems of this kind, why it is that there are generalizations in philosophy of science talk, projectable claims about large-scale systems that are not apparent or obvious from their microphysical constituents. So let's go back to the tiger. What could we do if we wanted to make more progress on coping? Well, we could say, look, the tiger is actually made up of cells which are organized into organs and which interact in various ways. And there are various robust generalizations that biochemists and zoologists have learned about the functioning of these various components of the animals. Those generalizations about how large molecules behave, about how fluids flow across cell walls and so on, had better not be incompatible with the microscopic physics. And every now and then they're going to go wrong, even though the microscopic physics is right, because some of the other things being equal assumptions we made in using them break down. But in general, it's going to be the case that if we try to run a description of tiger hunting patterns at the level of cells and organs, we're going to find it a lot easier to do than at the level of atoms and molecules, or electrons and subatomic particles even. So we've sacrificed a certain amount of precision and reliability for a vast increase in our ability to actually use the theory practically or explanatorily. It's still, of course, ridiculously difficult. Here's the third thing we could do. We could iterate that process. We could say that just as the cell is a complex system made up of lots of molecules and atoms, and just as we can write down generalizations about the cell that abstract from the details of the atoms, so we can write down generalizations for these whole agglomerations of cells and organs and things that we call a tiger that abstracts away from the fine details of the tiger's composition. And now we've moved away from the language of biochemistry and cell biology to the language of zoology, the language of evolutionary adaptationism, the language of evolutionary game theory. And this is, of course, the actual level at which we study high-level systems, because that's the level not simply that we can use practically, but at which we actually find the generalizations that we seek, where we find the robust structures and patterns which have robust dynamical laws of their own, derivable from the micro laws, but nonetheless autonomous in the sense that we can make predictions of that level without needing to constantly descend to the lower level. Level 3, of course, has to lean on level 2. The generalities of level 3 have to be true in virtue of the generalities of level 2, and the generalities of level 2 are better be true in virtue of the generalities of level 1. But we can't work directly at level 2, let alone level 1, without A, taking forever, and B, losing genuine understanding of what's going on. Here's the moral I take from that. The way to understand higher order ontology, not the electrons and quarks that make up our most fundamental physics, well, actually them too, but that's a side comment, but at least maybe not our most fundamental material, but all of our higher level stuff, our chairs, our tables, our cats, our dogs, our tigers, we should understand those in terms of patterns and structures. So for something to be a tiger, is for it to be a structuring of the physical world that displays tiger-like behavior, that satisfies the generalizations pertaining to tigers. Here's a source for that. Some of these ideas are an adaptation of ideas of Daniel Dennett's in a very important paper from about 20 years ago called Real Patterns. Paraphrase Dennett, this isn't a direct quote, this is a paraphrase. High-level objects are patterns or structures, and the salience of a pattern as a real thing, the degree to which it's legitimate to regard it as part of our ontology in its own right, depends on the usefulness, the power, the reliability of theories that admit that pattern in their ontology. Why believe that? Fundamentally, naturalism. The claim is naturalism is the position that ultimately science is our best epistemic route at getting at the world, and we don't have extra scientific grounds to reject the methods of science as a whole. The methods that science uses and with enormous success are committed tacitly or less tacitly to this kind of claim. And so in trying to understand higher order ontology in general in science, objects in science that are not part of the most fundamental ontology of our science, we should understand them in structural, pattern-like, functional terms. Okay, so now apply that back to the cat. What makes it true that some physical system contains a cat? At the most fundamental level, I've got my poor cat sitting in the box. There's really a sort of story about the behavior of that system of particles in the box just in terms of physics, just in terms of how the atoms and electrons inside the cat behave. At that level of generality, I won't notice the cat at all. But there's a higher level at which I'll see important generalizations. So as I go up to the level of animal physiology, I can predict, for instance, the cat won't spontaneously catch fire. I can predict that when the cyanide gas is released, the cat will die and its organs will stop working. These are all predictions I couldn't really make at the microscopic level, not in practice, and in terms of getting the generalizations right, not really even in principle. It's because I'm allowed to make them that I'm justified in talking about the cat cells and organs. And I can also make discussions at the level of the whole cat. So the cat is probably not going to start eating itself. The cat is probably going to jump back when the cyanide gas is released. In general, I've got a whole tacit or explicit theory of cats. And it's the fact that this system instantiates the theory of cats for the value live cat that makes it true that there is a live cat in the box. It's that this schematic thing abbreviates the description of a highly structured microreality that's cat-shaped that makes it true that I'm allowed to call that state the alive cat state. And likewise, it's the fact that such description applies to me that makes it valid for me to call this state the I see alive cat state. And similarly, it's the fact that this state is highly structured in the appropriate ways that justifies me calling it a dead cat state. Okay, but what about this state? This is our strange superposition state, remember? Well, this state is now has two separate lots of structure in it. This chunk of the state is highly structured, and it's got the kind of structure which licenses to say there is a live cat present. And this chunk of the state is also highly structured, and it's got the kind of structure that licenses saying there's a live cat present. So, thank you. not even a typo there. License me saying there's a dead cat present. So there are two entirely separate bits of structure in this state. And because cats are too big to do interference experiments, these two separate structures will not in some way reinforce or cancel out in the way that the photon interfered with itself. They'll just carry on being independently, separately present in the sort of highly structured totality of the quantum system we're studying here. So if the criterion for saying there is a cat present is that some part of the relevant physical reality is cat structured, then there really are two cats here, a live cat and a dead cat. So the multiplicity comes into our theory not at the level of fundamental ontology, but at the level of the way that ontology is structured. Where do I go from here? Yeah. So how am I doing for time? I think let me close my description of the first problem, the problem of ontology there. So the problem of probability, which is the one that's had the greater piece of attention in the philosophy literature, is going to be my topic this evening. I won't say any more about it now, but I will take the last few minutes to say a little bit about that third issue, the problem of absurdity. Here's a starting point. People may well have come across Occam's razor, the idea that somehow simpler theories are better in some respect. Here's William of Ockham. I understand that this quote is probably, although it's the way he's normally attributed, it's not actually findable in his extant works, but it seems to capture the idea. Entities must not be multiplied beyond necessity, says Ockham. So if there are things in your theory that you don't need to make your theory work, take them out. But Ockham conspicuously doesn't say entities must not be multiplied beyond a certain point, even when it's necessary. Necessary entities are fine for Ockham. And if you look at the way in which our methodology of science has worked in general, you really can see something like Occam's razor playing a role in our theories, but it's playing a role for a preference for simpler theories over more complicated theories. And it's playing a role in saying when there are bits in your theory that are just spinning wheels, that aren't part of the explanatory structure of your theory, then you should simplify your theory by removing those parts. But it's not, and has never been, a rule that just says we can't have ridiculously large additions to our ontology for the sake of explaining a small amount of data, if that ridiculously large addition to our ontology is part of a a maximally sort of simple and unified account of that data. Now, why do I say that? Because it's already happened. The theory that the solar system is alone in the universe, in terms of its predictive power, is really great. It gets most stuff right. The only thing it doesn't get right, as a matter of prediction, is a few very small dots of light on the sky. They're collectively less bright than the moon. A very, very small tweak to our theory to put the stars in. But in response to the fact that we'd like just to explain this small flaw in the solar system is alone in the universe theory, we postulate this kind of thing. If you think about modern cosmology, there are 100 billion stars in the Milky Way. The Milky Way is one of several 100 billion galaxies we can see. Vastly more that we think is there but we can't see. The sheer scale of the cosmos as described by contemporary astronomy is mind-bogglingly, vastly beyond anything that I think we can actually hold intuitively in mind. And that includes vast amounts of that theory which are completely unobservable. So our best theories of cosmology and astrophysics make claims about the existence of grains of sand on the beaches of planets orbiting stars in galaxies that are so far away that we can only see them as dots in good telescopes. We would reduce the ontology of our theory of cosmology very substantially if we decided to say, whenever planets are as far away as that, let's just take them out of the theory. Suppose there aren't any such planets. We'd significantly reduce the amount of stuff our theories claim exists if we did that. But Occam's razor clearly doesn't tell us to do that, because those entities are necessary entities in the sense that they're part of our best, simplest, most explanatory, powerful account. Is this different? Well, ontologically it's a lot bigger still, but I think if we tried to frame any reasonable maximum ontology before we started doing modern cosmology, we'd have exceeded it a long time ago anyway. It's hard to see the motivation of that. Is it stranger? Well, yeah. I mean, these distant galaxies are distant and strange, but they haven't got copies of me walking around doing things like me. Some of the real counterintuitive force of the many worlds theory is the idea that somehow it's not just the sheer scale of the universe, but that I personally am constantly branching into copies, and there's constantly many, many more versions of me out there that I don't know anything about. That is wildly counterintuitive. Here's Dan Dennett again. Most sciences, there are few findings more prized than a counterintuitive result. This is a quote. It shows something surprising and forces us to reconsider our own often tacit assumptions. In philosophy, a counterintuitive result is typically taken as tantamount to refutation. There's not a lot of good motivation for that. One of the really clear lessons of 21st and even more so 20th century physics is that the world is wildly counterintuitive. Our intuitions are an incredibly bad guide to what the world is actually like. We knew this even before we started running into parallel universes and many worlds. And that's not very surprising. There's no reason to think that our intuitions are set up for these purposes. Our intuitions were evolved to help us scratch a living on the savannas of Africa. The universe is not obliged to conform to our intuitions. I'll stop there. So the theme of the second lecture is very much to pick up on the second of the two serious objections I raised to the Everett interpretation, to the many worlds theory in the previous lecture. You recall the first objection, or the first concern, was exactly how we could understand the question of what justified interpreting these superposition states as multiplicities, and I argued that in that situation we need to understand the right theory in general of how higher order objects like chairs and tables and cats and dogs are to be understood in our physics, and just apply that framework to the mathematics of quantum mechanics. But the other problem, and the one that's had rather more attention in the literature here, has been the question of how we make sense of probability in the many worlds theory. And you can sort of break that concern into two. You can think that, firstly, we're not really sure how probability even makes any sense in the many worlds theory. So the theory seems to be a theory which involves deterministic branching. If I ask, what should I expect in the future? The answer is I should, with 100% certainty, expect to be a version of David who sees the cat alive. And in addition, I should expect with 100% certainty that there'll be a version of David that sees the cat dead. Now, it's true that each individual version of me will see a perfectly definite state of affairs. No version of me will see anything that contradicts quantum mechanics predictions. But the difficulty is that quantum mechanics is supposed to be making probabilistic predictions. So how we're to even understand those probabilities in a context where everything happens is unclear. That's the first problem. And the second problem is to say, even suppose we understand what probability could mean in the many worlds theory, how do we understand the quantitative numbers associated with the probabilities? So for instance, let's suppose I exaggerate Schrödinger's moral lackings and take a very large sample of cats and repeat these experiments with the interference, let's say, set so that according to ordinary quantum mechanics, every time I run the experiment, there should be a 2/3 chance of killing a cat. So now I run the experiment 100 times. The many worlds theory predicts a myriad branches for any possible combination of which cats live and which cats die. There will be some branches with that set of combinations on them. But quantum mechanics predicts that I should feel it's highly probable that about 2/3 of the cats are dead. Well, when there are branches where all the cats are dead, branches where half the cats are dead, a quarter of the cats, none of the cats, it's not clear in that framework how I can understand how the probabilities are linked to the actuality of what's described in the physics. It's certainly not possible to simply suppose that the probabilities can be connected in a simple way to the fraction of worlds. There's no simple way, that is, to say, well, what I mean is that in nearly all the worlds, 2/3 of the cats die. That turns out not to work. So those two problems, which often get called the problem of incoherence and the quantitative problem in probability in the many worlds theory, have exercised a lot of the debate in the last 15 years on this topic. And there's been a rather sneaky move that advocates of the Everett interpretation have made here, which their critics would say is a move they appeal to at the drop of a hat, which is to say, this problem that we, the critics, claim is a peculiar problem of the many worlds theory is actually a general philosophical problem that's just been cast into sharp relief by the unfamiliar surroundings of the many worlds theory. And that underhand trick is more or less what I intend to play right now. So what I want to do for the next half hour or so, really, is talk not so much about probability in the many worlds theory as about probability in general. And I want to get across the fact that probability in general is a very thorny and difficult philosophical question. While we know how to use probability, pragmatically speaking, in science, to understand what probability is a very hard ask. And I'm actually going to attempt the sort of judo-like move of saying not only is probability no more of a problem in the many worlds theory than it was previously, actually the many worlds theory gives us some resources to understand probability that were not available to us in the non-quantum mechanical context. That's the prospectus. Let me make a start on that. So the first thing to say if we're talking about probability is that it seems to come in various sorts. And one of the standard dichotomies that the philosophy literature draws is to distinguish between subjective probabilities and objective probabilities. So subjective probabilities, which sometimes get called personal probabilities, and which sometimes get called credences, are supposed to be something peculiar to the particular agent. They're measures of an agent's degree of confidence in some hypothesis or theory. And so it's perfectly coherent for, let's say, Harvey and I to have different personal probabilities of a given occurrence. Objective probabilities, which sometimes get called chances, are supposed to be something different. They're not supposed to be something about an agent's relation to the world, not something about my beliefs. They're supposed to be something about the world itself in some sense. And let me illustrate that and also illustrate that it's not a completely unproblematic distinction by giving a few examples. So here we have something that is very much on the subjective probability side. The probability of Labour winning the next election is 2/3. Now you can quantify these numbers, you can talk about them. if you've got a view about how likely it is Labour will win the next election, then Ladbrokes and John Williams and people will want to talk to you. Betting shops will cash the odds of these things and will pay out according to the results. And insofar as we can understand those numbers at all as more than just the playing out of a social activity, then if I say I think Labour's 2/3 likely to win the next election, I'm expressing some degree of confidence in it happening that somehow expresses the fact that I'm more confident in the proposition than its negation. And indeed goes further than that and quantifies how much more confident I am with the proposition than its negation. But if you were to say the probability of Labour winning the next election is 1/3, it's not obvious that we're disagreeing about some fact. It's not obvious, that is, that there's a determinate, true answer to the question of how likely it is that Labour will win the next election. After all, we know that's only going to happen once. Here's a borderline case. If I say this coin is fair, I seem to be saying something somewhat objective. If I say, if I roll 2 fair dice, the probability of getting 2 6s is 1 in 36, I seem to be saying something objective. Now, it's not completely clear what I could mean and what that objective thing could be, because both of those systems seem to be deterministic. That is, it seems to be that if I knew the starting physics of the coin or of the die, then I could predict with certainty the result of the throw, of the toss or the throw. And in fact, at least in the case of coins, that's not even a hypothetical. There are machines which will flip coins in a way that will look remarkably random, but which will land heads every single time. I'm told you can actually teach yourself to do this. It could be useful in some contexts. And yet, in another sense, it does seem that there's something objective about the claim that the coin, that if I've got fair dice, the probability of them landing double six is 1 in 36. The entire business model of Las Vegas is built around the fact that we seem to be able to say objective, robust things about probabilities of random events like the fall of dice, the playing of cards, the landing of roulette wheels. Here's a even more solid case. It's a little smaller than I intended, sorry. Quantum mechanics itself, and in particular nuclear and particle physics, seems to deliver very specific, very precise, quantified, measurable claims that nonetheless seem to be statements of probability. The probability per minute of a neutron decaying is 0.068. That doesn't seem to be an expression of my opinion. It seems to be saying something about neutrons. If a decaying nucleus of plutonium, if a nucleus of plutonium-240 decays, the probability of that decay being a spontaneous fission event is 5 times 10 to the power of 8, 10 to the power of minus 8. Very unlikely, but actually sufficiently likely relative to what happens with plutonium-239 that we seem to have discovered an objective difference between plutonium-239 and plutonium-240 that makes a difference to what we can do. And it seems that these are not simply expressions of our own uncertainty or curiosity. These are somehow very objective features of pieces of physical reality. And indeed, if we know these objective facts about these objective pieces of physical reality, we can make predictions and constructions. We can do technological things, experimental things. We can do some terrible things. That's Nagasaki. The project of building the atomic weapons in the Manhattan Project relies pretty strongly on what seemed to those project workers to be pretty solid objective facts about the uranium and plutonium nuclei that were involved in the work they were using. Okay, so the subjective probabilities are perhaps not so problematic, but the subjective probabilities don't seem to be the things that are turning up in the physics. They don't seem to be, I should say. That can be challenged. It seems, I've tried to make the case, that there is some objective notion of probability, some robust thing that looks factive, that looks like the kind of thing we work with in our science and measure in our science in roughly the same way we measure masses and charges, at least at a very broad level, that seems to be playing an important role in our doing physics, and that seems to be playing an important role in particular in our doing quantum physics, leaving aside entirely the many worlds theory for the moment. But that concept, that objective concept of probability, is mysterious. Let's break that mystery down a bit and see why it's mysterious. We can distinguish two questions to ask about objective probability, which are notoriously very hard to answer. And I'm going to call those the what question and the why question. Now, here's the what question. What, if anything, is the categorical basis for probabilities? And when I'm saying categorical in that sense, I'm using that in the sort of metaphysician sense. What are the, if when I talk about that sample of plutonium or that neutron, and I say about that thing that it's just objectively true that its probability of decaying or fissioning in a certain period is such and such a number, then what thing about that neutron makes it true? It's not its mass, it's not its charge, it's not its height or its width. What kind of actual objective things in the world, what kind of physical properties that a system can have, can make it true that its probability of behaving in a certain way is such and such? And then there's a related question, the why question. Suppose we found something which, formally speaking, has the right kind of properties to play the role of probability. Is that enough by itself to make it probability? Well, surely not. The area, if I take a sheet of A4 paper, or sorry, if I take a sheet of paper that's 1 metre square, then areas of subregions of that sheet of paper obey the calculus of probabilities. Formally, mathematically, they have the right features to be probabilities, and yet they are not probabilities. Those things don't seem to be the things we're talking about when we talk about probabilities. So the why question is then, once we've identified something in the objective physical world, which is supposed to be that in virtue of which a probability claim is true, we need to ask, why is that the case? How is it that those physical facts are sufficient to make that thing a probability? That framework probably looks quite abstract. Let me leave it there as a sort of set of guide rails and show you how that works in a bit of detail. So let's start with the what question. Here's a very tempting idea about probability. Probabilities are relative frequencies. So it's tempting to say, if I were to say, for instance, that a given neutron has probability 1/6, or let's say a die has a probability 1/6 of landing 6, what I mean is something like this. If I throw it 6 times, it's going to land 6 once. Well, that's a terrible account, of course. If I were to roll a die 6 times, of course, on average, I get a 6 once, but I might get more 6s, I might get fewer 6s. I'd be crazy to suppose that just because I've rolled a die 6 times and I've got a 6 twice, I should thereby conclude that the die is not actually a fair die, that the probability of landing 6 is not 1/6. So the temptation is to say, fine, let's roll the dice many more times than that. Let's roll it not 6 times, but 600 times. And if I roll the die 600 times, I would expect that I'll get a 6 about 100 times. But notice again that word about. What do I want to say about the situation where I get 200 6s? Do I want to say that's impossible? I don't think so. What I want to say, I think, is that if I roll a die 600 times, then getting 200 6s is very improbable. And that's a problem. Because the idea of my project here is to understand what probability is. And I want to make it definitional of a die having probability 1/6 of landing 6, that if I roll it 600 times, I'll get about 100 6s, then I don't have the resources left to say only if I roll a die 600 times, I'll probably get 100 6s. That won't do as an analysis of probability. If we understand probability independently of frequencies, then of course that gives me the resources to ground such a claim. If I know already what probability is, and I know how probability is connected to frequency, I can understand the claim that a certain set of frequency results is probable. But if I want to understand what probability is, defining it that way is not really going to help. Okay, so I could say, well, let me define probabilities in the infinite long run. Let me say, as I roll the dice more and more times, the fraction of sixes will get closer and closer to 1/6. So if I were to roll the dice 600 billion trillion quadrillion times, I'll get awfully close to 100 million billion quadrillion sixes. Okay, so there's a technical problem with that and a conceptual problem. Or perhaps in a sense, two different conceptual problems. Here's one problem there. If I were to roll the dice, here's what would happen if I were to roll a fair die 100 million billion quadrillion times. It would sort of disintegrate. So when I say that, when I say that I'm going to roll the dice that many times, I can't be talking about something that's ever supposed to be happening in the physical world. I must be talking about some kind of hypothetical scenario. And it's a quite surreal, it's quite bizarre hypothetical scenario. It's a hypothetical scenario where dice are indestructible. And it's tempting to say that's just sort of loose talk, and that actually what we're appealing to is the sort of ideal properties of the dice. But of course, if what we're appealing to is the ideal properties of a dice that has probability 1/6, if that's what we mean by it being an ideal die, we're begging the question. We're failing again to give an analysis of what the probabilities are. So that's one problem with that infinite long-run strategy. The other problem is it would be great, suppose we can understand an infinite long run, it would be great to be able to say, well, as a matter of mathematics, then in the long run, probabilities tend to relative frequencies. It would be great, that is, if there were theorems in maths to that effect. Unfortunately, we can't prove that in the long run, relative frequencies converge to probabilities. What we can prove is that in the long run, relative frequencies converge to probabilities, probably. And so again, this is great if we already understand probability and we just want to analyse its statistics. But if we want to analyse and understand and learn what probability is from thinking about frequencies, we're going to find it a very difficult task. Okay, but if probabilities aren't frequencies, what can they be? Because the nice thing about frequencies is they do at least seem to be something objective in the world. They're nicely categorical in my previous terminology. But what are the alternatives? Here's the main alternative that gets offered as to how we can understand what probability is. Probability's got something to do with symmetries. So one of the things you might have seen in school, if you remember being taught probability in maths, or if you teach probability in maths, is that the reason it's true that the probability of the die landing 1/6 is there's 6 ways it could land. That by itself is not a good argument. Here's why not. Take the die, paint 5 of its sides red and 1 of them green, and ask what's the probability that it lands green when you throw it. And according to that reason, the answer is 1 in 2, because there's 2 ways it could land, the green way and the red way. Something went wrong there, didn't it? So you might think, well, really, when you said there was 1 way it could land that was green, really there were 5 ways it could land. But that's not true. There were infinitely many ways it could have landed. It could have landed this way round, this way round, this way round. It could have landed over here, or it could have landed over here. Counting possibilities is not going to get us there in this situation. What's really going on, I think, when we say that there are 6 possibilities, is that there are 6 indistinguishable probabilities, 6 probabilities that should be regarded as somehow equipossible. And I think our grounds for saying that is something like, well, the die is symmetric. I can rotate one face onto another. And that's a symmetry, furthermore, that's respected by the laws of physics. If the die's pips are made of iron, and if the die is in a strong magnetic field, then the probability of it landing 6 is going to be rather a lot higher, or rather a lot lower rather than 1/6. So that what's going on is that the die has a certain symmetry with respect to the physics it's in. Even that's not quite enough, though. I mean, notice that, so just as a warning that something's puzzling here, suppose I take a die, I hold it with the 6 facing up, I hold it a millimetre above the ground, I let go. Doesn't matter how symmetric it is. You can be pretty confident it's going to land 6. And that points to the real problem with this sort of frequency approach. The die lands one way rather than another. Either lands 6, or it lands 1, or it lands 2, or whatever. So the physical situation can't be completely symmetric. Something has to break the symmetry. Because if nothing breaks the symmetry, then it can't be the case that one thing happens rather than another. So in the case I've just described, the symmetry, it's clear the symmetry is actually broken by the initial condition. And it's obvious how that works. If I were to drop the die from a great height, then the dependency of how the die lands on its initial condition is very complicated and very sensitive to the initial condition. And so in that situation, it's going to be very hard for me to predict how it lands, but it's still going to be the case that some feature of the initial conditions can't be completely symmetric because somehow the symmetry has to go away. Marie Curie has a principle, what's come to be called Curie's principle, symmetry in, symmetry out. If I get an asymmetry in my final situation, I must have put it in somehow. Okay, so those are two attempts to analyse what probability could be. Here's a third sort of attempt. This is Tim Maudlin in characteristically diffident style. He says, if someone complains that he does not understand the notion of physical probability, then I am tempted to respond with Dr. Johnson, I have found you an argument, I am not obliged to find you an understanding. That is, I cannot deny the possibility of a sort of cognitive blindness that would make someone unable to understand the notion of probability being used here, and I cannot offer a remedy for such blindness. Don't be bashful, Tim. Tell us what you really think. So Maudlin is saying, and it's a perfectly given thing to say, look, effectively you have to have some primitive somewhere. We understand how to use probability. Those who claim they don't understand probability, says Maudlin, are in a minority. We might not be able to analyse it or reduce it to anything else, but explanation's got to stop somewhere. There have to be some primitives in your story. Let probability simply be primitive. Let there be no analysis. Let's answer the what question by saying probability is part of the unanalysable starting furniture of the world. So much for the what question. Let's think of the why question. So the question here is, if you like, what makes something probability? What is probability, and how does probability connect to other non-probabilistic things in the world? And David Papineau has a very nice analysis of this, where he says, really, when you break it down, there are two links between probabilistic claims about the world and other claims about the world. There's a link from the world to probabilities, his inferential link. There's a link from probabilities to the world, his decision-theoretic link. And the inferential link basically says the way we work out what the probabilities are is by counting frequencies. So if I want to determine what the probability of the die landing 6 is, the way I do it is I roll the die many, many times. If I've rolled it n times and it's landed 6k times, then tentatively I conclude that the probability of it landing 6 is k over n, or about k over n, and the more times I roll it, the more confident I am of that assertion. So that's the inferential link, probabilities from frequencies. And the decision-theoretic link is that knowing the probabilities guides my actions. If I'm told that it's more probable it will rain in July than in August, other things being equal, that's a good reason to hold my wedding in August. If I'm told such and such drug has a higher probability of alleviating my back pain than such and such drug, that's a good reason to take the first drug. If I'm told various things about the probabilities of outcomes and I'm considering how to bet, in a slightly more quantitative way, the probabilities are guides to my actions and my betting preferences. And Papineau says, look, these are the ways in which probability connects to the world, and by the way, we don't understand how any notion of probability has those features. Here's a slightly more systematic way of doing what Papineau does. This is due to David Lewis. Lewis helps himself to that earlier notion of subjective probability we talked about earlier. And Lewis says we understand subjective probability basically fine. It's a measure of our confidence of hypotheses. And the way we understand how objective probability figures into our theories is we understand the link between objective probabilities and subjective probabilities. And his link is called the principal principle. Indeed. And roughly speaking, what the principal principle says is, if you know what the objective probability of something is, that had better be your subjective probability as well. In other words, you shouldn't be able to say, says Lewis, well, the objective probability of this die landing 6 is 1/6, but I'm going to bet at 2 to 1 odds that it's not going to land 6. Okay, it's the wrong way round, but I'll bet it 2 to 1 odds that it'll land 6. If I say, look, the objective probability that's happening is very low, but I'm really sure it's going to happen, then, says Lewis, you're acting irrationally. And you can sort of turn that round and say that for something to count as being objective probability, it had better be the kind of thing such that if I know what it is, I set my subjective probabilities equal to it. And there's a slightly more subtle statement of it that says something like, the subjective probability I give to a hypothesis, conditional on the objective probability of the hypothesis being P, is also P. And it turns out that if you buy Lewis's principle, you can derive Papineau's inferential and decision theoretic links from it. The price for that is you have to accept the concept of subjective probability, which not everyone wants to buy. Right, but how do we answer the why question? Let's look at frequentism. So suppose that suppose, never mind how, that I really know the frequency unto the end of time with which this die is going to land 6 when I roll it. Okay. And I know that if I roll this die, let's even be more generous, I know that over the next 100 million times this die is rolled, 1/6 of the time it will land 6. Okay, but I wasn't planning to roll it 100 million times. I'm planning to roll it once and call it a day. So if I want to decide, shall I bet on it landing 6 or not, why is it of the faintest interest to me what its long-run frequency pattern is going to be? And a way of making that vivid is, if we're defining our frequencies ad infinitum, well, the long-run frequency of something happening, averaged as the number of repetitions goes to infinity, is completely independent of the first time I throw it, or the first 10 times I throw it, or the first 10 to the power of 74 times I throw it. Any finite initial segment of an infinite sequence has no effect on the average value of something over that sequence. So it's really unclear, even if we had a frequentist understanding of probability to answer the what question, even if we could look at the world and from the frequencies extract some numbers which have the formal properties of probabilities, it's really unclear why those should have anything to do with our betting practice. That is, it's really unclear why the decision theoretic link should be true. And it's equally unclear why the inferential link should be true. It's equally unclear, that is, why, if all I know about, if all I'm after is an infinite long-run average, that I can get at that by saying I'll just sample a finite part of it. Now, there's space to get around that by saying, well, look, okay, there's space to get around it by the standard philosopher's trick of solving a problem by demonstrating that it is equivalent to the problem of induction, which, since we can't solve, is therefore a sort of panacea moves. So you could say, sure, I can't explain why the first million tosses of the die are going to look like the rest of the tosses of the die, but, you know, that's the problem of induction. I kind of have to assume a certain regularity. And that's fair enough. The difficulty, I think, is the sort of regularity I want to describe is one that we know how to handle and how to describe through the language of probability. And that really takes us back to the what question. It's not obvious we've got a story to tell about how to analyse the world in a way that makes sense of that kind of regularity, which abstracts away from that notion of probability. It's even less clear, I think, why we should accept the principle or the inferential decision theoretic link on Magdalen's primitive conception of probability. In fact, Lewis is quite upfront about this. He says, is there any way that any Humean magnitude, and he roughly means frequencies, could fill the chance role? Is there any way that an un-Humean magnitude could? And he kind of means something like Magdalen's primitive probabilities. What I fear is that the answer is no both times. So the temptation then is to say, well, this concept makes no sense. He goes on to say, yet how can I reject the very idea of chance when I know full well that each tritium atom has a certain chance of decaying at any moment? That's worth saying, if we could make the symmetry line of reasoning work, we might have a rather easier route to understand the answer to the why question. Why should I bet 1/6 on the die landing 6? Well, because somehow if the world has some objective symmetry, it doesn't really make sense for my own preference structure not to respect that symmetry. But we saw that the symmetry route is also running into big problems. So claim, where do we get to here? Yeah, both the what and the why question are actually really rather profoundly difficult to answer. We really are in a very difficult position in philosophy of trying to understand what probability is. We have no really solid, agreed upon strategies, and we have profound difficulties with most of the strategies on the table. So profound that many people are willing to actually bite the bullet and accept that it's all just primitive, that there's just no answer to these questions, just a basic brute fact. Others are willing to bite the bullet and say, even despite the apparent way probability operates in our science, nonetheless, there are, and when I say of the tritium atom it has a certain chance of decaying, I'm not really saying anything about the tritium atom. I'm somehow coding my beliefs. Let's look at quantum mechanics. Here's how the Everett interpretation answers the what question. Remember, the what question is just to find something in the world which we are able to understand in terms other than probability, which has the right mathematical, formal structure to play the probability role. Quantum mechanics has such a thing staring at us. The amplitudes, the numbers in front of the terms in the superpositions, have the right mathematical properties to behave like probability. In particular, in the scenario where I have branching, in the scenario where I have macroscopically distinct strands of physical reality that basically don't interfere with one another, then the behavior of those numbers over time obeys the probability calculus and obeys the rules for updating probability in the face of new data. And that's important because in the Everett interpretation, these things are categorical magnitudes. They have precisely defined mathematical role in the dynamics of the theory. We don't need to define them intrinsically in some probabilistic way. We can't even state the theory without these numbers being in it. The mathematical structure of the theory, insofar as this is supposed to be a physical way the world is, rather than, as we saw was impossible, an all statement, something codifying our ignorance, then the theory's got these built into its mathematical formalism in a way that isn't true of pre-quantum mechanical theories. What are these numbers? Well, if you want an intuition, it's not crazy to think of them as something like thickness of branches or number of branches. It's important to understand that's a metaphor. Really, to understand them, they're playing a certain mathematical role in the theory. It's a new sort of physical magnitude. But it's a physical magnitude which, in the right circumstances, that is, at the macroscopic emergent level, has the right mathematical structure to play the probability role. So, claim, the what question is actually in rather better shape in the many worlds theory than in pre-many worlds physics or philosophy. Oh, the why question. Well, you notice that I said that the problem with the symmetry understanding of probability in ordinary physics was that something must break the symmetry because something must happen rather than another thing. Well, if you're paying attention, it might have occurred to you that that's, and I'm sure did occur to you, that that's not actually true in the theory we're discussing. In the Everett interpretation, it really is the case that the two symmetrically related situations are both co-present. The symmetry in the many worlds theory is unbroken. And that suggests rather strongly that we can actually understand the link between symmetry and probability as telling us why it is that the mod squared amplitudes, those numbers in front of the terms, act as the probabilities. The symmetries of the equations of the theory allow me to exchange terms in a superposition as long as the numbers in front of those terms have the same square. So there's prospect, and prospect that one can turn into formal mathematics, to understand how the symmetry probability link works in a way that just was not available to us in pre-quantum physics. Take that, as I suggested, if we had a resolution of what was going on in the case of symmetry, it might make us easier to answer the why question in the form that Papineau and Lewis offer us to us. And that hope turns out to be borne out. If you make reasonable assumptions, then Papineau's inferential and differential synthetic links, Lewis's principle are provable. For arguments that basically have these symmetry considerations at their core, arguments which I'm afraid I'm not going to try to go through at 9 o'clock at night, so at some level you have to trust me on the maths, you can actually derive the fact that these assumptions hold. I don't want to suggest that the assumptions going into those proofs are uncontroversial, but there are proofs of this nature out there. The first of them was developed by David Deutsch. Here's David. Here's his, perhaps perhaps immodest, but perhaps reasonably so, quote in his paper on this. Thus we see that quantum theory permits what philosophy would hitherto have regarded as a formal impossibility, akin to deriving an ought from an is, namely deriving a probability statement from a factual statement. This could be called deriving a tends to from a does. So Deutsch proved a result of this kind about 15 years ago. Since then, there's been a lot of work, quite a lot of that in Oxford, which has honed those results, formalised them, clarified some ambiguities, weakened some assumptions, connected it to some of the literature and decision theory. And we now have really rather powerful theorems which start from quite general decision theoretic assumptions of the kind that enter into our ordinary decision theory, which have as their conclusion that the way somebody who is considering the Everett interpretation as among the range of possibilities that could be true is going to treat mod squared amplitudes in the Everett interpretation as if they're playing the role of probability. That is, they're going to update their beliefs about those amplitudes by looking at frequencies. They're going to use those amplitudes as guides to action. So let me sum up. There's a weak and a strong defense of probability in the Everett interpretation. The weak defense is, look, probability is difficult, okay? Even if it were true that we don't really understand probability in the Everett interpretation, it's not as if we understood it anywhere else either. So if you're trying to say, I will select a theory that I will reject the Everett interpretation because it doesn't give us a good understanding of probability, you're kind of running a double standards. You know, it's kind of like saying, I don't know, I'm trying to decide what pet I should have. Shall I have a cat or a dog? Well, the problem with having a cat is I really don't like animals with 4 legs, and cats have 4 legs. So I better have a dog instead. But that's the weak defense. More excitingly, there's a strong defense. Yes, probability is really difficult to solve, but in the Everett interpretation, we can solve it. In the Everett interpretation, at the very least, we have answers to the what question and the why question that are much better than the answers we have in the pre-quantum case. So we've made much more progress, so goes this claim, in understanding what probability is in the many worlds theory than we had made in pre-quantum mechanical physics. And it turns out that resources that wouldn't have occurred to us to stipulate just on the grounds of solving the probability problem, that we postulated for entirely different reasons coming out of physics, those resources turn out to be metaphysically extremely powerful in order to help us understand what probability is. So then the claim would be that if you're worried about probability, that's a reason to adopt the Everett interpretation. Let me stop there.